Good morning. This is Unit 6, Day 2 Notes, and we're going to talk about Venn diagrams, laws of probability, and tree diagrams. So it says S is a sample space. That means that this is the big rectangle, is our sample space, represented by this rectangle, and A is an event that we represent this by a circle. The complement of A, or A prime, means the complement of event A represents the non-occurrence of A. So A prime is on the outside of A, but within my sample space still. So this is A prime. Note that the probability of A plus the probability of not A is equal to 1. X is an element of A. The number of elements in set A is n of A. So let's do an example of a set. We have this set 1, 2, 3, 4, 6, 7, and 11. If A is 1 and 3 and 11, then A prime, or the complement of A, is going to be the other numbers, like 2 and 4 and 6 and 7. This is just like a little bit of vocabulary. It says A union B is denoted this way. This means union, and this means intersection. The union in sets A and B means all of A, all of B, and the intersection. So or, remember the mathematical or means and or and or. So A N B or A NB denotes the intersection of events A and B. And this means that X, such that X is in A and X has to also be in B. So this is how we write it. So let's do an example. I just wrote some numbers in here. So this is my set. A is this circle, B is this circle, and I wrote some numbers in between. So, given these numbers, A has the set 1, 5, and A also has 7 in it. B has the set 6, 9, and B also has 7 in it. Now, A union B means all of A, all of B, and everything in between that they both have. So 1, 5, 7, and 6, and 9. And I'm not going to write 7 twice. You only write 7 once. I would also try to put them in order, so switch the 6 and the 7. I can do this one actually right now. A union B complement means everything that's not in this A union B. Well, everything else is 10 and 3 are not in, they're in my set, but they're not in the union of A and B, 10 and 3. So this is going to be 3 and 10. Try to write them in order. A intersecting B means what do they have in common? What is in the middle? Well, what they have in common is 7. And that's it. So my complete set is 7. Now the complement of 7 is everything else besides 7. So this includes 1 and 3. Even though 3 is out here, that's not 7, so that is included. 5, 6, 9, and 10. I don't know if I missed any. I think that's it. Now, A intersecting only B complement. First, I need to know what is B complement. Well, that's not B. So B complement is, this one only is 3, 1, 5, and then 10. So B is 7, 6, and 9. The complement of that is this. Now, we want to know where that intersects with A. Well, A has 1 and A has 5, and that's it. So this intersection is only 1 and 5. let's try this. It says the Venn diagram alongside represents the union of all children, the set U, sorry, of all children in a class. Each dot represents a student. The event E shows that all students with blue eyes. So this is all students with blue eyes. And this looks like it is 8 of them. There's 8 students with blue eyes. Determine the probability that a randomly selected child has blue eyes. Well, I need to know the total set then. It's going to be 8 plus, I think this is 15. And 8 plus 15 is 23. So the total number of children that we are sampling are 23 kids. And the ones that have blue eyes are 8 of them. You might be able to simplify this. Try to simplify it if you can. Now, it does not have blue eyes. That's going to be this part right here. So this is 15 over 23. Do not have blue eyes. The total is equal to the total number in this set is 23, just so we know where this 23 came in. Okay, I want you guys to try this one. Try number 3. They actually wrote it in there for you. You guys can try number 4. The addition law of probability. This is very important. If we have 2 events, the probability of A union B is a probability of A. So this is going to be my A, and this is going to be my B. The probability of A is this, plus the probability of B is this. But you guys see, we actually counted the intersection twice. We counted the intersection when we did A, and then we did it again when we did B. So that means that we're going to have to subtract the intersection of A and B. We have to subtract this once. So let's do an example. If the probability of A is 0.6 and the probability of A union B, so this is A and this is B, is 0.7, and the intersection of A and B is 0.3. So this is 0.3. Find the probability of B. Well, if the intersection is 0.3, then I have to subtract that from the probability of A. The whole thing of A is 0.6. So 0.6 minus 0.3. This gives us just this part of A, which is 0.3. So this part is 0.3. And all of A and all of B is 0.7. So 0.7 equals, this is 0.6 plus the probability of B. I'm just going to use this formula right here. So probability of A is 0.6 plus the probability of B minus the intersection, which we found also, minus 0.3. Alrighty, well, I can combine these. 0.6 minus 0.3, move it to the other side, and I get the probability of B is equal to 0.4. If our sets are disjoint, that means that they are not going to have any intersection, and that means that they're not going to have any elements in common. My formula does change a bit. Instead of A union B being probability of A plus the probability of B minus the intersection, well, if the intersection is 0, the intersection is equal to 0, then we just have the first two. Probability of A plus the probability of B. Okay, so you can just plug in 0 for the last term. I just want to make sure I didn't skip anything. A box of chocolates contains 6 with hard centers H. So 6 H's and 12 with soft centers S. So 12 S's. Are the H and S mutually exclusive? Well, yes, because you can't both have a hard and a soft center. Those are going to be completely opposite. So yes, you can't have both hard and soft centers. Okay, find the probability of H. Well, we've got to add them up. 6 plus 12 is 18. So out of 18 candies, the probability of having a hard one is going to be 6. You can simplify this to 1/3. I would. The probability of soft, well, we know that that's going to be 12 over the total, which is 18. I think this simplifies to 2/3. But the intersection of hard and soft, there's no intersection. These are disjoint. You can't have both. The union is 1. The union is 1. 6 plus 12 is 18 over 18, which is 1. Alrighty, let's go to conditional probability. Suppose we have two events, A and B. Then A, the probability of A given B, or A occurring knowing that B occurs. So let's do an example. So this little line, a vertical line, means the probability of A given that B does occur. In a class of 25 kids, students, 14 like pizza and 6 like coffee. So I made, I kind of started it. So these are the students that like pizza, and these are the students that like coffee. It says one student likes neither. So I put 1 on the outside of my circles. This is my set. And 6 students like both. So if 6 like both, in order to find out how many people only like pizza, I have to subtract that from 14. So what is 14 minus 6? I think that gives us 8 people like pizza. And I also have to subtract the 6 from the people who like coffee. But I know that 16 minus 6 is 10. That one's easy. Alrighty. What is the probability that a randomly selected student from the class likes pizza? Well, I know that there's 25 students, and if you add this up, it should now equal 25. The probability that somebody likes pizza, well, 8 people like pizza, and the 6 over here people like pizza. And in fact, 14 people like pizza out of 25. You can simplify this maybe. This is a probability of liking pizza. Likes pizza given that she likes coffee. So the probability of pizza given coffee is the probability that she likes pizza and likes coffee on top. So this is going to be 6. This is the probability of coffee and pizza divided by the people who like coffee. It says that it's given she likes coffee. Well, the people who like coffee are 16. I think you can simplify this to maybe 3 over 8. Let's look at conditional probability. We have a formula for this. We have a formula that we used right now on this one, part B. So the formula is, if we have conditional probability formula right here, or the probability of A given B is the probability of the intersection divided by the second one, which is B, which is what we did in part B above. So we can actually derive another formula for this. Sometimes we need to fill out different things or solve for different things. What I did is I just cross multiplied, put a 1 under here, cross multiply. The probability of A intersecting B is equal to the probability of B times the probability of A given B. And this also leads to, we can flip it. We can say, oh, this is also the probability of A given and then the probability of B given A. So we switch these two. That's okay. You need to switch this one also. It's always going to be the second one. If they are independent events, so this is our disjoint circles, the ones that don't overlap, then the probability of A intersecting B is the probability of A times the probability of B. Okay, this is only for independent events. Write it down. Let's try this one. So it says 50 students go bushwalking. I looked it up. It means hiking. Okay. 23 get sunburnt. So this is going to be my sunburnt. And 22 get bitten by ants. Bitten by ants. This is my set. And I made this by myself, so just draw your circles. 5 are both sunburnt and bitten by ants. Determine the probability that the randomly selected student, all of these things. Okay, so there's none that didn't get anything. Okay, so there's 50 students. I need to find out how many just got sunburnt. Well, if 23 got sunburnt, but 5 of them are in the middle, what is 23 minus 5? And that will give us our 18. If 22 get bitten by ants, but 5 of those also are sunburnt, so 5 of those go in the middle, 22 minus 5 is 17. And I'm actually going to add this up, and these give us 40. So there's actually 10 students left over that they didn't talk about out of these 50 students. So there are 10 that didn't get anything happen to them. Nothing happened to them. So it says, what is the probability that a randomly selected student escaped being bitten? Well, this is the probability of not being bitten by ants, so A prime. So it's going to be not A, so not 22, which is 28. 50 minus 22 is 28 over 50. You can simplify that. Was either bitten or sunburned. Well, we got to add them up. 18 plus 5 plus 17. I think I said that was 40. So the probability of bitten by ants or sunburned. Remember, the mathematical or means and or. So we're going to put 40 over 50. You can definitely simplify this one. Was neither bitten nor sunburned. So the probability of A union S, and then I'm going to use another set of parentheses, complement. The complement of this is going to be 10. So this is 10 over 50, or 1/5. Was bitten given that the student was sunburnt. So the probability of A bitten by ants given that he is sunburnt, which is the intersection A intersecting S, which is 5, over the probability of S, which is 23. Yeah, 23. Okay, I want you guys to try this one. If they are independent events, then the probability of A given S will be the same as the probability of A. Well, they will be equal. Alrighty, go ahead and flip your paper over. So note that for probabilities, oh, did we skip something? Okay, so we're going to start our tree diagrams right here. This is a tree diagram. A tree diagram, these are just kind of like a probability tree. Let's consider if Daniel takes 2 free throws in succession. 2 free throws in succession. What is the probability that he will make exactly one basket, and what is the probability that he misses both? So the question, part of the question got cut off. It says Daniel has a free throw percentage of 72%, and Madison has a free throw percentage of 80%. So I guess Madison might come up later. It says, what is the probability that he misses both? So we're going to make a tree diagram. The first one is going to be him making a basket or missing. He has a 0.72 that he's going to make the basket. But if you subtract this from 1, we get 0.28 that he misses it. Now, if this is the first basket we're missing. From here, if he throws another one, then he can either make a basket again, and this is going to be also 0.72, or missing, also 0.28. And this is making a basket or missing. And also, if he misses the second time, he can make a basket. He still has a 0.72 chance, or he will miss it, 0.28 chance. Now it says, what is the probability if he takes 2 free throw shots? What's the probability that he misses both? Or sorry, what is the probability that he makes exactly one basket and then that he misses both? So my outcomes, there's going to be some outcomes, 1, 2, 3, 4 outcomes, are the probability that he makes a basket and then another basket. And we're going to multiply these. 0.72 times 0.72 is 0.518. What is the probability that he makes a basket but then misses? Oops, basket and then misses. This is a 0.202, 20% likely. The probability also that he misses and then makes a basket should be the same. So misses and then makes a basket, or misses and then misses again. .0784. Alrighty, when we add these up, these should equal 1. The total should equal 1. Okay. So if you add up the probability that he makes a basket and then misses, or misses and then makes a basket, that's exactly one basket. These two will both give us exactly one basket. So this is the probability of exactly one basket, and this is 0.404 if we add them up, 404. So this is probably exactly one basket, 0.404. Now, the probability that he misses both is 0.0784. Or, if you move this over twice, 7.84%. Note that the probability for success and failure are marked in the branches. There are 4 alternative branches, and each branch shows a particular outcome. All outcomes represented and probabilities are obtained by multiplying along the branches. Remember, we're multiplying. Each path is mutually exclusive, so the probability should add to 1. You guys can try this one. If he makes all 10 baskets, then the probability of 10 baskets is 0.72 to the 10th power. which is actually small, 0.0374, something like this. So it's like he has got a 3.7% chance that he gets all 10. Alrighty, I'm going to try one more. So this is the independent and dependent events. If A and B are independent events, then the probability of A and B is going to be the probability of A times the probability of B. Okay. Dependent events, if they are dependent, then it's going to be the probability of A times the probability of B given A occurs. Okay. So suppose let's try this one. Suppose a hat contains 5 red marbles, 3 blue tickets. 5 red and 3 blue tickets. 1 ticket is randomly chosen and discarded. So 5 red and 3 blue. This is what I'm going to start with. My total is 8. So we're going to have 5 over 8, which is red. 5 over 8, which is red. And then 3 over 8 is blue. 1 ticket is randomly chosen and discarded. A second ticket is randomly selected. What is the chance that it is red? So if we first picked red and then we discard it, then we are going to have 7 tickets left when we choose again. And this is going to be my first ticket. And then this one is going to be my second ticket. So if I had chosen a red, then I'm going to have 4 reds left, and I'm only going to have 7 tickets altogether. And I will still have the 3 blue, but still 7 tickets altogether. So this is red again and blue for the second one. Now, if I had chosen a blue, I will still have 5 red, but there will still be 7 tickets altogether. And then there will be 2 blue out of that 7 tickets. So this is red again. Oops. Red. And then blue. So we are asked to find the probability of what is the probability chance that it is red? What is the probability of red? Knowing that the second ticket is red, what is the probability of the first is red? So we don't know what the first ticket was. It was just randomly chosen and discarded. It could have been red, but the second ticket that is randomly selected, what is the chance that it is also red? Well, it could have been red, or it could have been blue first and then red. And we need to find both. So red is 5 over 8, and then red again is 4 over 7. And I think if you multiply that, you get 20 over 56. Now, if you do blue first, which is 3 over 8, and then red, which is 5 over 7, that'll give you 15 over 56. So part A says, what is the probability that the second ticket is red? Well, the probability that the second ticket is red could happen either way. So we've got to add these. So 20 over 56 plus 15 over 56, which I think, I don't know, gives us 35 over 56. sampling with or without replacement, I'm just going to do this last one and then we'll be done. Sampling is the best process, or is a process of selecting an object from a large group of the objects and inspecting it, and that's noting some features. The object is either discarded, which means we're sampling without replacement, or returned, which means we're going to sample with replacement. Consider the box containing 3 red, 2 blue, 1 yellow marbles. Suppose we wish to sample 2 marbles with replacement and without replacement. Well, I'm going to try this one for you. So we're going to have 3 branches, 3 red, 2 blue, and 1 marble. We got to add those up. 3, so it's 6. So the probability of red, blue, and yellow. So 3 over 6 is 1/2. Let me just make it black. 1/2. 2 over 6 is 1/3. And then 1 over 6 is 1 over 6. With replacement. So we're going to put it back in. Now when we pick another marble, we're still going to have red, blue, yellow, red, blue, yellow, red, blue, yellow on each one, because we're putting them all back in. So red, blue, yellow, red, blue, yellow, red, blue, yellow. The probability for red is still going to be 1/2. It's not going to change because we put it back in if we pick the red first. And then this would still be 1/3 and still be 1/6. 1/2, 1/3, 1/6. 1/2, 1/3, and 1/6. Now, if we did not replace this, suppose we wish to sample 2 marbles with replacement and without replacement. So if we did not replace these, I'm still going to start with the same red, blue, and yellow. So red, blue, and yellow are still 1/2. Oops. One-third and 1/6. However, if we started with a red marble, then we only have 2 left. So this would be 2 over 7 though, or 5. And then we would have we still have 2 blue, and we still have 1 yellow. The red, blue, and yellow. Okay, now if we had a blue, so there's 2, there'd still be 1 left. So I can still do my 3 branches for red, blue, and yellow. So now there would still be 5, but my red would be 3. My blue would take away 1, so it would be 1. And my yellow is still 1. However, when we get to the yellow, we took it away. So we're going to have a red and a blue, but we're not going to put the yellow back. So we're going to have 3 red and 2 blue. But there would not be a yellow. That would be impossible. So notice that the probability of both reds is equal to 1/2 times 1/2, which is 1/4. But the probability of both reds in this one is 1/2 times 2 over 5, which is 1 over 5. I want you guys to try these. And if you have any questions, ask me. Have a wonderful day.